Hello, everyone. Welcome to pre-lecture 15. This is going to cover how we think about salts with regards to some acid-base chemistry, as well as some polyprotic acids. So based on, let's see if I can get my slides to go forward here. So based on what we've talked about in class so far, we've talked about acids, bases, how they react with water, and also some, at least, about conjugate acids and bases. And so in this pre-lecture, we're going to consider essentially how salts, or how things that are not necessarily named acids or bases, can also affect pH. And so, for example, if we have the salt ammonium chloride, then we need to consider the relative acid-base strength of the salt's constituent ion. So if we think about ammonium chloride, NH4Cl dissolving, we would end up with NH4 plus and Cl minus, right? The ammonium ion, if we highlight that, is going to be the conjugate acid of the weak base ammonia, NH3. And so it will actually undergo another reaction with water where it makes hydronium and NH3. And NH3 is now our conjugate base, with ammonium, NH4 plus being our acid, right? Alternatively, if we consider chloride, then chloride we know is the conjugate base of a strong acid, HCl. And so that means that it will, if it reacts with water, it would form hydroxide and HCl, but because we know HCl is a strong acid, we would say that the reaction is entirely going to favor the reactants. And so we will not see an effect on the pH due to the presence of the chloride, but only the ammonium ion, okay? Same could be true if we considered another example where we had something like sodium acetate. So this is the molecular formula for sodium acetate. If we first consider how it dissolves, we would get sodium plus and acetate minus, C3CH2, or CH3CO2 minus, sorry about that. We consider how each part will react with water. We should know that acetate is the conjugate base of the weak acid, acetic acid. So it will undergo an ionization reaction with water to form hydroxide and acetic acid, where acetic acid is now our conjugate acid, right? And we also have the cation, sodium, which we know is the conjugate acid of a strong base, sodium hydroxide, meaning again that our reaction will entirely favor reactants for this situation. And so the solution overall would end up being basic because we have only one ion that is going to react with water in any sort of meaningful way to affect pH. Okay. Right, and so let's go through some of the math for how a problem like this would go. And so in this practice problem, say I ask you to determine the pH of a solution that is 0.075 molar in sodium acetate. I give you the molecular formula there. I also give you the Ka for acetic acid. And so in this case, we know acetic acid is acting or is an acid, right? We have a Ka, but we might need to use something different for this reaction. And so my advice remains the same for how to solve all these sorts of problems. And that would be starting with writing out the chemical reaction that's going to be relevant, and then writing out the equilibrium expression. And so we can actually write two chemical reactions if we want for this. Since we know sodium acetate is a salt, the first chemical reaction we could write is just it dissolving. And so if we have Na2H3O2, we say that starts as a solid or as something aqueous. We know that because it's ionic, it's going to dissolve. And so we're going to make Na plus aqueous plus C2H3O2 minus aqueous. So that's our first chemical reaction, is this just dissolving to form its ions. Then if we look at our two species that we get sodium plus, which based on what we've talked about, we know is a conjugate acid of a strong base, meaning that this will not have an effect on pH. So we can essentially ignore that. but we also get acetate, which we know is the conjugate base of a weak acid, in particular acetic acid, right? We need to write a second chemical equation where, say, we have C2H3O2 minus reacting with water, H2O, which is, of course, a pure liquid, and that's going to be in equilibrium with the products. So if acetate acts as a base, it's going to form acetic acid. So we would add 1 proton to it, H3O2. That would still be aqueous. And then if it deprotonates water, we would, of course, end up with hydroxide as our conjugate base. And so this is where we can then write an equilibrium equation, or expression rather, for that. So we're going to say K is equal to, again, our products over our reactants. So HC2H3O2 times OH minus, and then that is going to be divided by our C2H3O2 minus. And we would ignore water because it is a pure liquid, right? So something I want to point out here is that we're given the Ka for this expression, but in this case, our equilibrium expression, the thing we care about, is acting as a base, right? Our C2H3O2 is acting as a base. And so instead of this expression being Ka, this is going to be a Kb expression, okay? And so we're going to need to take that into account when we start to solve for our equilibrium concentrations to ultimately determine the pH. Okay, but before we do that, we can build our ice chart. So we know water is a pure liquid, so I'm just going to cross that out. And if we build our chart here, we're told that our initial concentration is going to be 0.0750 molar of our acetate. And then because we're not told anything about our products, we're going to assume that their concentration is 0. We can subtract x from this side because we have a coefficient of 1, add x here, add x here. Then if we combine our first two rows, we get 0.0750 minus x, x, and x for our equilibrium concentrations, right? So the other thing we need to do that I kind of hinted at earlier is we need to figure out what Kb is. And so in order to do this, we can use our Kw expression. So a reminder that Kw is equal to Ka times Kb. And Kw is also equal to 1.0 times 10 to the minus 14. And so we can, if we plug in our values for Kw and Ka, we can solve for Kb. So Kb is going to be equal to 1.0 times 10 minus 14th divided by our Ka, which is 1.8 times 10 to the negative 5th. So I got a value for Kb equal to, let's see if I can actually find where I wrote this down, 5.56 times 10 to the minus 10. Okay. And so if we plug in our variables, x here, we could say that Kb is equal to 5.56 times 10 to the minus 10, which is equal to x squared. So I'm just plugging in our x values that we got in our equilibrium row into our unknowns for acetic acid and hydroxide. And that's going to be divided by our equilibrium row for acetate, which is our reactant. That would be 0.0750 minus x. If we look at our Kb expression, this is times 10 to the negative 10th, which is much smaller than 10 to the negative 4th. So we can say this bottom x is small, which means we can ignore it. So in order to solve for x, then we would multiply each side by 0.0750 and then take the square root of each side. So when I did that, I got a value for x equal to 6.46 times 10 to the negative 6th. And so that will be equal to both our concentration of both of our products. So concentration of acetic acid, which is also equal to our concentration of hydroxide. And so our final step here is to, again, we're asked to determine the pH. And so there are a couple of ways we can get there to determine our pH from our X value. And so with this, the way I'm going to do it is I'm going to say, again, 1.0 times 10 to the negative 14th is going to be equal to our concentration of H3O plus times our concentration of hydroxide minus. And so we have our value for hydroxide here. That's our value for X. We have our 1.0 times 10 to the negative 14th. So we can solve for concentration of hydronium. When we do that, I got a value of 1.55 times 10 to the negative 9th. And if we take the negative log of that, in order to get the pH, I got a pH equal to 8.81. Okay. So that's how you would solve a problem like this. We will do much more practice in class, but I hope that was useful in helping you understand how salts will affect the pH of a otherwise neutral solution. Have a good rest of your day. Please do let me know if you have any other questions. And don't be salty. I'll see you in class.